Yes. So thank you very much for inviting me to give a talk here. So I haven't given an offline talk for about more than a year and a half. Especially, like giving a talk in English after such a long break. It's gonna be very, I don't know how it's gonna go. So if I stumble, or if you have any questions at any time, just feel free to stop me. Okay. And it does. I have prepared lots of materials, but it doesn't matter because if you get lost, whatever I talk about doesn't mean anything to you. So feel free, just stop me so that you can at least learn something about from my talk. Okay. So also another thing, I like to use board, but haven't done it for a while, so I don't know how it's going to work out. So what I want to talk about, some particular, so my motivation is from the neural net. But actually what I want to talk about later is going to be characterization of certain types of linear functions. That's eventually what I'm going to talk about later. But here's a motivation about the topic that I want to explain today. So I'm not quite a mathematician, so my handwriting is not very good. So the motivation is, as you know, the neural nets, in a sense, revolutionized the day-to-day life. You will hear about it all the time. And if you want to apply for fundings, putting some terms about neural nets may help you. So lots of people are interested about it. But what are the neural nets? From the nutshell, the neural net is nothing but a parameterized functions that goes from some input space to the output space. Typically, input and output space are Euclidean space, R to the n, and then the neural net is parameterized by the parameter W. And the purpose of the neural net is that we are given some set called the training data. They are the input-output pairs. And then from this training data, we want to find the appropriate parameter W, such a way that Fw of xi becomes quite close to yi for every I. This is what we want to do through the training of the neural nets, and there are multiple algorithms that are designed to do this. So that's one objective. The second objective is, in doing so, we want this neural net to identify, it generalized well. We want it to identify some hidden patterns in my data set, so that although it's kind of explained in terms of input-output pairs, if they are really talking about some smooth functions, we want this neural net to identify the smoothness and so on. So we want this type of, in a sense, good fitting from the input to the output. At the same time, we want this neural net to generalize. Okay, so that's the very kind of quick review of the neural net. But then you can see that from this perspective, one thing you can immediately see is that, finding such a W is not going to be easy. So we have two objectives. One is it fit data set very well. Second, it generalized very well. And meeting that objective is not very easy because, usually the parameter space is really large. This is not an easy optimization problem. So one thing that people try to do is to incorporate some of the prior knowledge about the ideal function that we are looking for into this setup. And one of the things that people do is to identify some form of symmetries. So if the training set implicitly describes the function that we care about, but suppose we also know that the function that we care about satisfies certain properties, especially certain symmetries, which I'm going to explain soon. So then, when we design the neural net, the parameterized function, we can incorporate this idea of the symmetry into the design of the function directly. So here's some mathematical way, explanation about what's really going on. Suppose we have a group G acting on these two sets, X and Y. Okay, so I'm going to write G dot X to means that group action of the group G on the element X. And that group actions can be continuous group actions, like rotations and so on. Also, it can also be some discrete group actions, such as permutation. If X is a sequence, group G may permute the element of the sequence. Okay, so there is a group G, and group is acting on X. Then suppose that some of the prior knowledge that a designer of this neural net have is that my neural net preserves this symmetry. It's a bit more mathematical terms. What that means is this commutative diagram holds. If we have a X, suppose instead of Y, in this case it's just a real number. So this is the one way to explain or formalize this group action formalized symmetries, and this is a one way to say my function that we are looking for actually respect these symmetries. And there are actually examples. So although the actual implementations of CNN doesn't really satisfy the so-called translation invariant exactly, some idealized version that working on some infinite grid that satisfy this type of symmetry properties, where this X is the kind of, they satisfy this type of property, especially it satisfies something called translation invariant. But there are other examples. So imagine a neural net that working on sets. Okay, so then the typical implementation of a set in a neural net is a vector. It's as a sequence. Okay, but we want a function to working on set, which means the order of the sequence shouldn't really matter. So this G acts as a permutation actions on the sequence, and what we want is that we want the neural nets to be invariant with respect to that permutation action. Okay, so that's and then you can see that if you do so, because that imposes really strong conditions of f of w. Or another way to say it is we put kind of big prior knowledge in the design of what shape of the w. Maybe this the objective that we have. Train this neural net that fits the data set well, also generalized well. Maybe meeting that objective becomes easier. Okay? And we can kind of see that's actually the case. So instead of thinking about this, we're gonna look at some generalized version of this symmetry preserving, which say that we have an arbitrary set Y. This is also very good. And we will consider the case that this commutes for all change. Okay. So the previous case was R. This Y is equal to R. Group action was the identity action. This can be seen as a generalization. And people typically say this means f of w is G invariant, no, G equivariant. And let's see that whether this property actually simplifies something. So let's look at, just move to the next. So let's look at some simple examples where so suppose that X is equal to R3, and then now suppose that this f of W is a linear map that goes from R3 to R3, and then group G is a permutation actions on all these three elements. So if you act this group element, they will permute the components of the three-dimensional vector. Now, if FW is doesn't really respect, it doesn't have to be this G equivariance. The most general form of this FW, because it's a linear map, we can write it as a matrix. The most general form is going to be look like this. have a, B, C, D, F, G, H. So we have 9 parameters. But if F satisfies is a G equivariant, so this is a general form. But if FW is a G equivariant, it has to be of the following form. Be that all the diagonals should be the same value A, and all the rest has to be the same value B. You can see that there is a huge difference. Beforehand, there were 9 parameters. Now we have only 2 parameters. The kind of rough heuristics say if you only have 2 parameters, fitting 2 parameters is going to be a lot easier. And at the same time, because this type of form have this equivariance built in, it will capture our intention a lot better. That will translate into better generalizability. Okay, so that's the setup. So now what we want to do here, okay, so this is the general setup. Maybe just review. So the objective that we have, so we want to generalize what's really going on here from this sequence to a bit more structured data. Okay? So the kind of thing we want to do is that we want to design a neural nets that take as an input something like a multi-set of size 3 that has a bipartite graph. So because it's a multi-set of size 3, but then each of this is complete bipartite graphs. But then so they are all of the same shape. I mean, that's our result is dealing with at the moment, generalizing it with future work. But this is all the same shape. And then each of the edges have a label. The label is again multi-set of size 4. So the label for this edge may be 1, 2, 3, 4. Label for this edge may be 7, 8, 11, 4, and so on. Okay. So we have an input like this. And then we want to design a neural nets that take input of this form and return some number. Okay. It may be the return a number, but the things that I'm going to talk, ultimately return a number are, but the setting that in the setup I want to talk about, it's going to be a mapping that takes, in a sense, this type of inputs and produce a similar kind of output. But the labels of these edges may change. Okay, why we will care about this? Because a linear, we will think of this, in particular, we're going to think about linear map of this form, because by stacking these linear map, at the end, just putting one function that return a real number, we can build this G equivalent neural net for this more complicated input. Okay, but then in this setup, what we are looking for. Now, if you implement this one as an input, okay, then this first the multi-set will be implemented as a sequence. Okay, so we want this function to be, in a sense, insensitive with respect to the reordering of these 3 labeled bipartite graphs. So that's the first thing we want to make sure. The second thing, so this reordering, we want this function f to be invariant. The second thing that we also want to be sure is, now for each of these bipartite graph, if we implement this bipartite graph as an input, it's going to be represented as either adjacency matrix or something like adjacency matrix, which means that it implicitly give a name to each vertex. The first guy is named as the first vertex corresponding to the first row of the adjacency matrix. Second guy corresponds to the second row of adjacency matrix, and so on. But we want this input to be a bipartite graph, which means the reordering, or the renaming the vertex from the first row to the second row shouldn't really matter. So if you apply permutation here, and then another permutations on this side, again, we'll look at this equivariant version, so it will be more general. But really what we want to say is my function doesn't depend on this particular name that we give these vertices. So that means when we think about the perturbing it by using group actions, perturbation for the first two vertices here, the three vertices for the first bipartite graph, three vertices for the second bipartite graph, they have to be independent. If we are forced to apply exactly the same permutation, that doesn't entirely capture what we want to do here. Okay, one permutation here, another permutation here, yet another permutation here. Okay. Now, finally, because each of the labels is a multiset, we want our function f do not really depend on the order of this multiset. So the question becomes, okay, these are the kind of setup that we want to have. We have we can say highly nested data or maybe structured data. Then we want our neural net to preserve many symmetries that exist in the highly structured data. So the question is how we can formalize this and how we can design a neural net that have this type of properties. Okay, so that's the objective we have. And what I'm going to explain to you is I'm going to tell you how we can formalize this using a set. So there are some form of nesting. There is the outermost, we have a multiset, and then we have a graph, and then each label, in some sense, in the most case, we have another multiset. So there's a bunch of nesting going on. Then I'm going to formalize this using a DAG, so what I call skeleton DAG, that essentially describe how this layering of what's really going on, and then define appropriate symmetries that can be used to capture the symmetries that I'm talking about here. And then the other things that I'm going to explain to you is I focus mainly on the linear map here, and I will tell you what the linear map will satisfy become the G equivariant. And although the proof is like 80% done, and I have an informal argument later in a bit, but we believe that's going to be also complete characterization of the linear map that satisfy the symmetry properties. Okay, so that's what I'm going to do. So maybe so maybe just this is better. Right. So then now let's move to the next part. The second part is so I'm going to define what I call skeleton DAG. Which is used to specify the structure, whether this nested structure of my data. And then I'm going to tell you about DAG-symmetries. Which means that I'm going to define some groups. So what I'll do is talk about DAG, and then using DAG, I will define something called some indices with some structure, and then use it to talk about DAG there. Right. So, before talking about this, I think it's good to have a big picture about what's really going on. What's really going on is we will describe the space for the inputs using, we'll assume that that's going to be of this form, r to the I. Okay, so it's essentially a functions that's going to be the shape the shape of what my input space actually look like. I is an index set. And so each function describe for each index what value I have. So for instance, index set will identify a particular particular position of the multiset here. So you will say index set will identify the second element of the outermost multiset, and then this particular edge, which is the first vertex in this first partition, first vertex in the second partition, If you care about number 3, that's going to talk about there's a third element. So all these labels can be accessed by this index, which say which element of the outermost multiset we are talking about. That will give a first number, which of the vertex in the first partition, which of the vertex second partitions, and if that will identify a edge, and given an edge, there is a multiset again, then we will want to pick up some particular value there. So when I talk about multiset, I'm really thinking about this sequence representation of the multiset. Okay, so this is going to be general shape, and now what I have to do is and then we're going to have a group G, and then group actions acting on I. Yeah.
So when you say index set, that means so for each index you assign one real number, right?
Yes. So each index will identify this position, something like this. This means the second element, the index is a bunch of numbers. If the first component of the index will say second, then we'll identify this second bipartite graph. And then you will identify this edge by saying 1, 1. And then you will also identify the third element of this sequence representing a multiset, so it's number 3.
So it's like the sequence of the
yeah.
first coordinate represent like
right. That's right. Yes.
Well, what's this real number?
So the real number is this guy, number 3.
Oh, I see.
Yes.
So the number.
Yeah. Okay. So this is a kind of general shape, and just we'll mention one more thing and then go into more details. Now we're gonna define group G that we're acting on not this X directly, it will act on index. And then we will extend this group actions to elements X here. So that will return another X prime, which is a mapping from index to values. So if you access its index I, it's going to be X G inverse acting I. So this is something that we're gonna define, and then this is gonna induce the definition on the values. So if you don't understand this, that's okay, because we're gonna come back here. I just want to tell you the big picture. So now that the real meat of what I'm gonna talk about is how to define I. So I is defined, I and G, and then this group actions. I is defined in terms of a DAG. So we're gonna assume a DAG, it's a finite DAG, D. So we'll assume that we are given a finite DAG D, and then we'll assume that this is what I call skeleton DAG. So that will describe the nesting structure. It's not about index. It's to describe how things are nested with each other, which things are not nested with each other, and so on. So in our example that I'm going to explain here, our DAG will look like this. There's a 4-vertex diamond shape. The top one describes the outermost multiset in some sense. These two guys are identifying the vertex of the first partition, vertex in the second partition. The one below identify specific elements in the multiset attached to an edge. Okay, so that's the shape, and right. And then now how I'm going to define an index. We call the so I will assume there is a function k that take vertex, return finite set. Okay, so the one example is for our examples, what this k does is that for the first vertex, it roughly saying what's going to be the size of the multiset and what's going to be the size of the vertex set and so on. The first one will be mapped to set consisting of 1 to 3. That's because we are thinking of a multi-set of size 3. And then this vertex is going to be mapped to 2, because in our bipartite graph, there are 2 vertices there. And this for 3, and this for 4. So that's our K. And then the index is defined to be I write it as a dependent function. So what that means is for each vertex, we will return an element in K of V. So one example can be, so we have this diamond shape. So I will omit this arrow will go down. The first one maybe, just look at this, number 2. This vertex get mapped to number 1, finite, number 3. So each of the vertex is the values in the set in the K of V. And then this one identify this position. This is specific position. Okay. So that's the index. And now we have to define G. Now defining G turned out to be quite challenging. That's because one of the reasons why it becomes challenging is because this is G. Okay, so let me start with, for G, we will start with the following things. For each of the vertex, so we will assume that let's say for T of V is a group acting on K of V. So suppose, one thing that we can think about is, for our example, the K, this T is T for transformation. So T for this vertex, let's call it V1. Maybe it's permutation group on S3. And this is V2. T for V2. It's a permutation group S2 and so on. So each of the vertex we have groups. That you may think, oh yeah, if we have a group for each of the vertex, the index have the same shape, you can just apply it directly. That doesn't work. Why that's the case? The reason is, if you do so, that means we have one permutation actions for each of these vertices of this diamond, especially if we have one permutation actions on this, this vertex V3. That means we're gonna permute these vertices in bipartite graph and these vertices in bipartite graph, these vertices in bipartite graph by the same group action. That's not what we want. We want group actions here, here, here to be different. Okay, so that's what makes things more complicated here. So now how to do this? So to do so, we're gonna use something called some generalized version of wreath products. So the group G, let me first write down, G is defined by, again, dependent functions. So for each vertex, we return something. But then this dependent function is not just K of V, but it's a, you can say, family of K of V, or it's a mapping from something to K of V. When I explain what this is, so A of functions from A of V to K of V, where A of V is it's a set of ancestors of V. Okay, so what does that mean? Slightly more formally, some vertex W such that there exists a path of length greater than 1 from W to V. So that means that we have not just a single I mean, if so, we have not just a single the group elements, but we have a bunch of group elements there. So I think the best way to understand what G is to see an example. So let's think about once. So no, sorry, I use H there. So very likely I will forget what I wrote and maybe stick to my, it's not K, so H. So this is what I have. So then what are the example here? Example, I mean, it's not quite example, but the typical element G, that will look like this. It's going to be a map from this DAG to something. The first one, this A of V becomes a singleton set. I mean, although it's not quite written that way, it's a singleton set. So in the first V, because it doesn't have any ancestor at all, so we have the only one, the group actions H, which is H of 1, which leaves H of V. But then, yeah, but then I think my definition is exactly what you said, but we did as if it doesn't have any ancestors, it should be a singleton set. I mean, yeah, so that's how I should have defined here. Yeah, right. So this is just H1, and then for here we have a H2, but we have not just a single H2, but H2 indexed by the all of these. No, sorry. This is the reason why it doesn't work is like this. It's an index restricted to ancestor. Okay, it's not A of V. It's an index restricted to the ancestor. So that's why if it's an empty, it's a singleton set. But I think looking at the example is actually better. So here we have not just a single group element, but we have a family of group elements. So because the index set for the top is 3, we have 1, no, this is 3, it's 3 of 2, 3. I mean, the superscript 3 is because of the vertex 3. I mean, see this vertex 3. And then for this vertex, we have similarly have H2, 1, H2 of 2, H2, no, so 3 here. Okay, so we instead of just 1, we have a 3. That's because its ancestor, which is this node, can have a 3 indices for that vertex, which is 1 to 3. Okay, the one bottom can have quite a lot of group elements there, and the group elements are H of 4, 1, 1, 1. So this 1 is for the index for the roots, 1 is for the second vertex, 1 for the third vertex. You can go all the way to for the 3, 2, 3. So you can have something like this. And then if you restrict attentions only to these 2, that's exactly what people call wreath product. Okay. Right. So that's our group. And then we have to define the group actions there. The group actions right. Group action for the index look like this. So if we have this type of element G, as I said, I'm going to define how group act on the index first. Then that will induce the definition that I wrote on the top. And let's define like this. G applying the index I. So I is something like this kind of thing is an I. and G acting on I at vertex V will be defined by, essentially it's applying. You look at the vertex V, that will give us not a single group element, but bunch of group elements. And we will select something among this bunch of group elements, and then we will act that element to I of V. So for instance, this G of V will return something like this tuple, and the subscript J will pick one of them, and then we will apply this one of them to I of V, which is the number that you see like 1, 1, 2, and so on. Okay. And then this dependency on this J is what allows us to use the different permutations for the different bipartite graphs. Okay. So then how to compute J? And this J is defined by G. So this is defined inductively. So you can, so we restrict G to all the ancestors of V, and we restrict I to all the ancestors of V, and we inductively apply this G to I to obtain some element J. So roughly speaking, for the index, what we do is that we apply essentially G to the corresponding part of I to pick up the appropriate index J here. Okay. So then, I mean, you might say where this actually come from, and this is actually coming from the definition of the wreath products. And so, right. Then just one more thing that I say, and I said this X, I'm not going to define the inverse and so on. It's gonna take quite a while, and then none of you will be able to follow this. Instead, I'm gonna tell you about this G applied to X and I. Okay. So what it does is that it takes X and then I think still it's not comprehensible. So G inverse. So you don't need to understand G inverse I, but let me just define G inverse I. So it's defined like this. The inverse I acting on this G inverse acting on I is, I mean, I say this is a bottom-up approach. I think maybe the best is to show. I still don't feel like you can understand what's going on here. Maybe the best way is to show some picture. So let me draw something like this element X here. So then we have because it's a multiset of size 3, we have a 3, this arrow that goes to the outside. And then we have 3 bipartite graphs. Of course, looks like this. And then each element, this is kind of adjacency graph, but what's inside this adjacency graph is 4 elements. Okay. It goes like this. So now which means that typical X will look like this. Have a value, so value stored here, maybe 5, and 21, and so on. So, and this is a representation of X, and index will identify appropriate positions in here. Now, yes. Right. So if we act, where is H? Yeah. So this particular G on X, then here's how it works. Okay, it's essentially a top-down algorithm. So you look at this X, and I pick H1 to permute this top 3 element according to H1. This is permuted first by H1. And then after the permutations, and then after the outcome of the permutation, maybe this index may becomes from 2, it will move to 3. Okay. So this entire thing will move to the next. So something like this. Now for this, we now have to pick permutation for the rows and columns. Then our choice will be based on the outcome of the permutation. So number 3 will be used to pick this guy and then this guy. And then this H2 subscript 3, H3 subscript 3 will be applied to here. So these things will be permuted. And after the permutation, things will be rearranged. And now to pick appropriate permutation for each box, that will be applied to, after the outcome of this permutation. So we first permute this outer, the top level, and then using the index of the outcome of the permutations, we permute the row vertex and column vertex. And then after the permutations, we identify each cell, and the cell will tell us which of these H with the 3 subscript should be chosen. That will be applied to there as well. Okay. Okay, so just to this, although looks complicated, essentially it's a top-down algorithm. Starting from this, apply the permutation, and then we just go top-down. Now let's hope I didn't really argue, but this is to give a proper kind of way to capture or express the kind of symmetries that we care about. So then now what's going to be the symmetry-preserving transformation? So that's the last part in 15 minutes. So we have what symmetry preserving linear maps in this context actually look like. So we have X, which is I, and we are only thinking about this X to X. And then we are looking for a linear map F that satisfies this property. For all G. So, for computer scientists, what we are looking for is that we want some nice way of constructing such F. And also we want to show that our particular way of constructing F is complete. It will give us all the linear maps of this form. Okay. So then what's going to be our constructions? So the construction is based on Kronecker products. So for the setup that I explained here, so we are thinking about, so I'm not going to give a general explanation, but I will just explain the specific things that's going on here. So for each of the vertex, we are associating a linear map. So for here, this is V1, V2, V3, 4. For V1, we associate linear map V1. That goes from the R to the K of V1 to R to the K of V1. So then F3 R to the K of V2, R to the K of V2, and so on. So they are all the linear maps. Now, if you have all these linear maps, they're going to be a matrices. It can be represented as a matrices. And if you take a Kronecker products, that can be made to work on R to the I. Why? Here are just some rough kind of calculation that may convince you. So if you compute the dimension of R to the I, so dimension is equal to essentially cardinality of I. And the cardinality, this is defined by K of V. So this will be essentially a product of cardinality of K of V. Right. And then for the Kronecker products, each of these F of V, so for instance F of Vi, will work on R to the K of Vi to R to the K of Vi. So if you take a Kronecker products, it's going to work on the products. V3. Then if you compute this dimension, that's actually the same, but if you compute the dimension, that will be exactly as K of V. Okay. So it's not a proof. What I meant is, if you have a linear map for each of the vertex, you can put them together to produce the linear map for the entire space. That doesn't generate all the possible linear map, but it can, if you do the linear combination, that can generate everything there. So now, what our main results tell us is the following. You say that our main results say, now suppose, because for each vertex, in some sense our setup is very well decomposed. For each of the vertex, suppose we have a linear map like this. And also, one thing we have is, for each of the vertex, we have a group actions. So H of V1, that acting on K of V1, that can be made to work on this value space, R to the K of V1. Here we have a H of V3, so H of V2, and so on. So each of the groups can be made to work on this value space for each of the vertex. So one possible good candidate is that if all of the F of V, like F of V1, F of V3, F of V4, F of V2, and so on, if all of them are, they are equivariant with respect to group actions for the vertex KV1, HV1, here HV3, and so on. So then the Kronecker product, maybe it also preserves this equivariance. Okay. So, but it turns out that's not always the case. So 5 minutes, so it's a sufficient condition. So if f of if that's we want that is Kronecker products. Turns out that's not really the case. We need one more condition. That condition say, actually this we have to strengthen this condition as follows. The condition says something like this. If you look at our DAG, suppose this is our DAG, I mean, we should be able to find some anti-chain in this DAG. So something between two elements in this anti-chain, we can't reach from one from the other. So there's an anti-chain in the chain, in this DAG. So, and then above the anti-chain, there's a ancestors of this anti-chain, and there's a rest. Okay. So the conditions say for everything that goes above this anti-chain, f of vi should be an identity function. And let's use red. And then everything here, we don't put any condition at all. So this equivariance is good enough. Now things go below. This f of vj here. It has to be, as a matrix, it has to be a matrix which contains 1 everywhere. Okay. So if we satisfy this, each component are equivariant, and then there is an anti-chain. Above the anti-chain, we have an identity. All the rest, the anti-chain plus the above, and except that everything should be essentially identically one's linear map. If that is the case, so then the Kronecker product becomes G equivariant. So that's the result that we have. And I mean, the proving this is not very difficult. If you just do the calculation, you can do the proof. Then we believe that this is actually if you take all these such equivariant map, there's not just a single, but lots of them. If you take all these equivariant map and consider their linear combinations, so equivariant maps, their linear combination is also equivariant. If you consider all their linear combinations, our completeness results, which we believe to be true and almost proved, say that also covers all the possible linear maps. So every G equivariant linear maps. Every G equivariant linear maps can be expressed in terms of linear combination of such a guys. So that's our other result, which is a bit more difficult to prove. So this is sufficient conditions, and the other cases kind of completeness. Say if then as a linear combination of those that's expressed in the theorem. So that's our completeness result. And for this, we have to do some form of counting. We just said dimension of span generated by this G equivariant map of this form is the same as dimension of all the G equivariant functions here. And it can be proved by induction, but requires some more careful tracking. Okay. Right. So actually that's all I want. Maybe I have 1 minute. I can perhaps tell you about what needs to be done next. And a few things that needs to be done next is, now I talk about right. So one of the motivating example was like this multi-set of the bipartite graphs. But typical things that you play with are not bipartite graph, but just graphs. Okay. Then can we express the set or just a setup such a way that what we have is not this multi-set of bipartite graph, but this multi-set of graphs, which means really when we think about what that means is when you define this group G, So when you define this group G, I mean, we have to restrict this group G. So this group G, I mean, if this vertex, there are three vertices here, I mean, we are allowed to use a different permutation on the vertex on this side, the vertex on the other side. We have to impose a condition that the permutation we are applying has to be exactly the same. So that requires, instead of using this G, we have to construct its subgroup, which is using some techniques. Okay, I mean, we have to construct some subgroup here. The second, what we really want is we want multi-set of arbitrary size, and also for the graph, we don't really want to say all the graphs, bipartite graph are 3, 3, 3. We want to put some, we want to consider some setup so that it can work on the multi-set of arbitrary size graphs of a bipartite graph of arbitrary size. So how can you do it? So that's the second question that, I mean, that we perhaps want to work on. The final thing is that, I mean, I didn't implement anything, so just implement something based on some of the theory here, and then see whether that really leads to some useful kind of neural net with a new architecture. So that's the last bit that I want to work on. Okay, so that's it today, and thank you very much. Yeah. So this is say this linear map that working, I mean, that goes from this R to the I to R to the I should be constructed in a certain way. It should be constructed as canonical products. 그냥 한국말로 설명할까요? 아니면 영어? It's a canonical products. And each of the components, like f of vi, so in the canonical products, has to be HVI equivariant. So in a sense, we decompose the problems for this DAG into each of the vertex, and say for each component it has to be equivariant for each of the vertex, but it has to satisfy one more condition. Then one more condition is there has to exist an anti-chain of the DAG. For this case, the anti-chain maybe include these two. And then the conditions say things above the anti-chain that has to be, so FV1 in this case has to be identity linear map. And things, and the not above, not in the anti-chain, all the rest has to be the essentially linear, the matrix represented by 1 everywhere, which is essentially a summation matrix. If you apply it, it's a sum all the components together. So that's the condition, and it turns out that condition is good enough. I mean, that condition is sufficient in some sense, sufficient and in some sense necessary. Okay.
How restrictive is the additional condition?
So for in terms of the if, as I said, this completeness we didn't really prove completely yet. But if you think if it's true, if it's true, what that means is it's complete. I mean, it's as good as we can get in the sense that any G equivariant linear maps can be expressed as linear combination of these canonical products. Yeah.
Taking R for base view?
There's no reason. I mean, because I mean the neural net often the value stored in there is a real number, but it can be in
R, then we can more feel free to use some representation theory of finite groups.
So that may be possible. So because my knowledge on math is very limited, so that's why we just do it. But you're right. I mean, it's a good suggestion. If we use C, then maybe we can have a nicer representation. That may also still be very useful result in this context.
Well, I understand that this is a layer, right? So you can stack this layer into a deep,
Right.
I guess, equivariant networks.
Yeah.
Do you have any ideas on what would depth mean in terms of generalization or other aspects?
So I have no idea. So usually if you stack these things, I mean, often this linear layer is interleaved with nonlinear layer. A nonlinear layer is applying some nonlinear operation pointwise or component-wise. Okay, and then typically what happens is that once you go higher and higher up in the layer, you start to identify some bigger kind of what people call features. So initially you may be describing some aspect, some local aspect, if you go up and up, it try to capture some more global aspect. Whether that always happens, I don't know. That's typically what people observe. So if you go up and up with this constraint, it will likely behave the same way. But how equivariance will affect what kind of feature we discover, I have no idea.
Any other questions? So it's not the same for speaking.